All right, hello everyone. Welcome back. Today we are going to be talking about limits of a function. So just a reminder for limits, how do they work? Limits have to do with the behavior around a certain point. So for example, a limit as x approaches 3 of 4x subtracting 2, right? This has to do with not what happens exactly at 3, but what happens around 3. Now, what happens around 3 and what happens actually at 3 will be the same thing in a lot of cases, right? In so many cases, what happens at a number and what happens around a certain number, approaching that number, closing in on that number, is going to be the exact same, essentially. The only times when it might not be, and we might have to dig a little bit further, might be if the exact value is undefined, but the values around that value that are very close will be still defined. So we'll get to that in example D, but actually for A, B, and C, these are pretty straightforward limits. We can just plug in 3 because it's the limit as x approaches 3 in this case, and we will get 3 times 4 minus 2, which is 12 minus 2, which is 10, and that's the answer. And same thing with B. We can just say this is the same as 1 over 4 plus 3, which is 1 over 7. Voila. And then for C, same thing. We can say this is 3 times 2 squared plus 4 times 2 minus 1, which is 3 times 4 plus 8 minus 1, which is 12 plus 8 minus 1, which is 20 minus 1, which is 19. Now, how about D? You'll notice if we plug in 5 right away, we'll get on the bottom 5 minus 5, which is 0, right? And we can't have 0 in our denominator. This isn't allowed, right? Something else that isn't allowed is we can't have a negative number in our square root, right? It's undefined in that case, unless we're going to go into the world of imaginary numbers, which we're not. So in this scenario, what can we do, right? We know 5 is not defined, but we don't actually care what happens at 5. We don't care that 5 isn't defined. That doesn't mean there's no limit, right? What that means is we have to ask ourselves, are the values around 5 defined? Like, for example, 5.000001, is that defined? Well, yes, because then in the denominator, we would have a value very, very close to 0, but not actually 0, right? We're allowed to have values that are very close to 0 as long as it's not an actual 0, then that's where we get into trouble. So what I'm going to do here is I'm going to see if I can simplify this a little bit further. You might notice that the top here is actually a difference of squares, and we can factor it to get x minus 5, x plus 5, like that, over x minus 5, and then we can cancel, and we get limit as x approaches 5, x plus 5, and now we can actually just sub in and get that this is 5 plus 5, which is 10. So the limit is 10. So even though f of 5, right, if this was our f of x value, if this was our function, f of 5, to be clear, would be undefined. It would not be 10. However, because we're not finding f of 5, we're finding a limit as x approaches 5. It does not matter that f of 5 is undefined because we only care about what's happening right around that point. And if we think about it, all this x plus 5, this is just a line, right? This is a line that starts at 5 and goes up with a slope of 1, right? So it has the point on it here, 5, 10, right? It has this point here, right? 5, 10. However, in this scenario, 5 is undefined, so we would actually have a hole here in this case, right? So this is a line with a hole in it at x equals 5. So you might notice how all the surrounding areas getting really, really, really close, it's approaching in on 10, right? Even though f of 5 is not 10, right? F of 5 is undefined because there's a hole there. So that's kind of the idea I want to get across. And I mean, let's say the line had, didn't have that hole in it. It was just a regular old x plus 5 line that didn't have these other steps in the beginning that we had to do. Well, in that scenario, f of 5 would be 10, and the limit as x approaches 5 would be 10. And in most general continuous functions, that is how it's going to work. We only get into trouble if we have a hole somewhere or some other sort of discontinuity that makes it so that our limit doesn't actually approach the value that we think it should, right? Or our limit approaches a value that we think, oh, maybe it shouldn't approach. So let's talk about how do we know a limit exists. So basically, if a limit exists, that means that the right-hand limit and the left-hand limit must both exist and must both be the same. So I'm actually going to go back to this example here. I'm going to hopefully draw a bit of a better drawing this time. Okay. Well, that's not that much better, but that is okay. So here we're going to start at 1, 2, 3, 4, 5, right there like that. This is 5, and that's 10, and this is 5. We got another point right there that actually is a hole. It's a hole, not a point. And here is my line with a hole in it. So the limit as x approaches 10 from the left, right, the left-hand limit, let's see what that is. Well, if I go from the left, right, here's my left hand, let's go from the left to the right. Oh, we stop right around here, and it's approaching 10, right? And now let's say we come from the right going towards the left, which is this limit here, right? Same thing. We're approaching 10, right? So from both sides, the limit is 10. So therefore, the limit exists and the limit is also 10. If one or both of those limits did not exist, then the overall limit would not exist. And if these two limits, the limit as x approaches a from the left or x approaches a from the right, if those two things are different, then the overall limit would not exist. In this case, it does exist and it's 10 because both are approaching to 10, right? And please note the little plus here and the little minus, this indicates from the left and from the right. So this little L, or sorry, this little minus sign means from the left, and this plus sign means from the right. Okay? So from the left or from the right. Otherwise, the limit does not exist. So basically, let's say you're asked to tell, does a limit exist or not? You're going to test this criteria. You're going to ask yourself, is it true that the left-hand limit and the right-hand limit are the same? If they are the same, then that means the limit does exist, and the limit is the same as the limit that both sides approach to. And if that is not true, either because one or both sides does not exist, or because there's some sort of a discontinuity there where we jump from one spot to another, whatever the case may be. If those two limits, the left hand limit and the right hand limit, are not the same, then the limit does not exist. So basically, we're looking for, is this true that the right hand limit and left hand limit are the same? And if it is true, the limit exists. If it is not true, then the limit does not exist, or you can write DNE for short to say does not exist. Here it says use the graph to find out if the limit as x approaches 3 exists for this function. Well, let's see. Let's see if it exists. So let's see. Let's first look for the left-hand limit. So limit as x approaches 3 from the left of f of x equals. And then let's test the limit as x approaches 3 from the right, and let's see if they're the same. So let's first approach from the left going towards the right. So let's see. In this case, as assuming each unit here is 1, we get to 2, right? So the answer here is 2. Now I'm going to go from the right to the left. So starting here, oh, we stop at 2, right? Because keep in mind this point is 3, right? We're stopping at 2 again. So therefore, the limit does exist. And the limit is equal to 2 in case they care. In this case, they actually just asked whether it existed or not. But in case you care, the limit is 2. All right. Let's try some other examples. Here it says, draw f of x and determine the limit as x approaches 1 in this piecewise function. So let's do this. So the first part of the piecewise function, actually I'm going to do this middle step first, where it says that f of x equals to 1 when x equals to 1. So that means we have a point here at 1, 1, because that's what it says. The next part says, right up here, it says x minus 1 when x is less than 1. Well, we know that the x minus 1 graph starts at -1, and then it slopes. It has a slope of 1, right? So our next point would be here, except that we only go this far, right? We only go this far, and we keep going downwards. So what I did here, right, is for this piecewise function, I drew just part of the graph, right? I drew just part of the graph. Now, if you're having trouble with piecewise function and drawing them specifically, there's a whole lesson on that in the grade 12 advanced function series. And then this next part is root of x minus 1 plus 2. So I'm actually going to draw the full graph of that, a little sketch of it. So recall how normally our function would look like this, but in this case, we're going to move it to the right by 1 and up 2, right? So right 1 and up 2. So our vertex, or not vertex, but our starting point is actually here, and it's going to go off this way somewhere. I don't actually care where the other points are for this example. So the question is, does the limit exist? Well, let's see. You might already be able to tell, right? But I'm going to show in more details. So limit from the left, and then the limit from the right. So let's go with the limit from the left first. So limit from the left to the right. So this one is, 0, right? 0. And then the limit from the left, from the right to the left. Let's see, 2, right? 2. So therefore, the limit does not exist, or DNE for short, to say does not exist, because the left-hand limit and the right-hand limit were not the same. Now keep in mind, this step I still drew on my graph because it was here. However, it didn't actually make a difference whether, f of 1 is equal to 1. It doesn't matter in terms of the limit. I don't care what that is. What I care about is the fact that when we look for the right-hand limit and the left-hand limit, they ended up being at different values. They did not end up being in the same place, which is what we would have needed in order for the limit to exist. Let's try this next one here. So this next one, our first point is 1, 4. Actually, I'm going to just draw some tick points first. Okay, so 1, 4, like that. And then we have x plus 3 for when x is less than 1. So that's going to be here. And it's actually going to go to here. And now normally we'd have a hole here, right? But it's already filled in due to the fact that we have f of x is equal to 4 when x is equal to 1 anyways. So that's why it's filled in, even though it wouldn't be according to just this step. We fill it in because of the step 2, okay? All right, then let's move on to the next part. 2x squared plus 2. Well, the starting point there at x equals to 1 is going to be 4, so it's actually going to start here as well and go like this, right? It's going to do some sort of opening up, right, at some level. We don't actually care exactly how it opens up. We just need to know that opening up going this way, right, to draw a somewhat accurate type of graph. Okay, so now let's figure out if the left-hand limit and the right-hand limit are the same. Okay, so the left-hand limit, the limit as x approaches 1 from the left is, let's see, 4. The limit as x approaches 1 from the right is, also 4. So therefore, the limit exists And in this case, it said determine the limit, so we actually would have to say what the answer is in this case since it exists. The limit as x approaches 1 of f at x is 4. Awesome. All right. Let's try this one here. This one says sketch the graph of any function that satisfies the following given conditions. Okay? All right. So this first one says f of 5 is equal to 2. Okay, so f of 5 is equal to 2, right? So when x is 5, y is 2. So that's our first point. The second one says the limit as x approaches 5 from the left is 1. So that means we must have a hole at 5, 1, right? Now, why can't it be a filled in point? Because we already have a filled in point for this vertical line, right? For this invisible vertical line right here, we already have a point, and we know that a function can only have one for each, right? We know that a function must pass the vertical line test, otherwise it is a non-function. And this is written in function notation in all three places, which suggests to me that it must be a function. And it's coming from the left. So we can draw anything we want here. I'm just going to draw a straight line. You could draw a squiggly line. You could draw a quadratic, whatever. As long as it comes from the left, that's the most important thing. Then we have this point here that says a limit as x approaches 5 from the right is -2. So let's go, oopsie, down to -2, -1, -2. Oh, keep erasing stuff. There we go. And I'm going to draw another hole, and this one is going to go to the right. It doesn't matter if it goes down to the right or whatever, or up to the right, but as long as it's going to the right, right? Because it must come from the right when we're going to close in on 5. So there you have it. There you have it. And keep in mind, these aren't the only two answers. It is key that this section here specifically must look the same as my section here did, right? However, these lines don't have to be lines. They could be squiggles, they could be, whatever you want, as long as they come from the correct direction is the important thing. And so this is a function here that satisfies all three of these conditions. So I advise you guys, after you're finished doing a question like this, double check. Does it satisfy condition 1? I'm going to check. Let's see. 5, 2. Yes, it does. Does it satisfy the second condition that as x approaches 5 from the left that we get 1? Yes, it does. And does it satisfy the condition that the limit as x approaches 5 from the right is -2? And again, yes, it does. So we can give that one a check mark as well. All right, well, that is it for today. Next time, we'll be talking about the properties of limits, but that is it for today.